moving on to section 2 of chapter 12 with probability. Last week we kind of talked about basic probability. Talked about mutually exclusive. What does mutually exclusive mean? Or you can give me an example.
There's two things that don't correlate.
Right. There's two events that have nothing in common. Can someone give me an example of that? Pulling a card and flipping a coin. Do those have anything to do with each other? No, they're two different things, right? Kind of similar with independent and dependent, right? What does it mean to be independent? By itself, it doesn't depend on something else, right? Dependent is when, for example, if I draw a marble and I don't put it back, that changes the probability for the second draw, okay? So that's kind of a little bit of what we talked about last week. Today, we're going to be talking about conditional probability. Okay, and a little bit more on dependent events, but majority we're going to be focusing on this conditional probability. Okay, so first, I just want to talk about this one. It says, at Central High School, 85% of all senior girls and 65% of all senior boys attend in the spring dance. Of all attendees, 20% won a prize. I just want to ask you, is it likely that the person that won a prize is a senior? Why would you say yes? Right, 85% are senior girls, 65% are senior boys. So do you think it's pretty likely that a senior is going to win? Yeah. Yes, because we talked about this last week. If it's more than that 50% mid-range, it's probably more likely than not. Okay? So let's get into conditional probability. Here it says a student committee, and this is the same table that is in your example 1. Says a student committee is being formed to decide how after-school activities will be funded. The committee members are selected at random from current club members. The frequency table shows the current club membership data. What I want to label real quick, this side right here, this is an event. Go ahead and label that on your paper. And this side right here is another event. Okay, so we're comparing two different events or options that are happening. So, for example, reading this table, how many total juniors do we have?
39.
How many?
40.
Right. Juniors here, our total is 40. How many total science do I have?
40.
That 40, right? How many sophomores are in art? 24 out of how many sophomores? 36. So that'd be 24 out of 36. How many of the art students are seniors? 18 out of?
150.
Okay, I'm glad you brought that up. This 115 is the total of the whole table.
No.
Okay, but if I asked you how many art students are seniors, you would tell me 18 out of the 58, because 58 is the total art. Okay, so a little practice with frequency tables. This one says, what is the probability that a member of the art club, so member of the art club, is selected at random as a junior? 16 out of 58, right? Because there's 16 juniors out of 58 members of the art club. Okay, and then of course, like down here, we would reduce that when we can. Okay, I want to point something out real quick. What does it mean by selected at random? We see that a lot. What does it mean by selected at random? Right. Is there bias? What does bias mean? It's like an opinion. So if I said that math is the best class in the school, am I pretty biased to that? Why? Because I'm a math teacher, right? If Johnson says PE is the best class in the school, is he pretty biased to that? Yes. Okay, there has to be facts behind all this stuff. So selected at random, that means there's no biasy happening. You don't know what's going to happen. Okay, so go ahead and look at your example. I'm going to stay on this page so that I have the table to look at. But your part A and B, go ahead and answer both of those, and then we'll talk about them together. Do a different word. So in your part A, it has it written in this form here. Yes, it says it in words, but I want to talk about what this means. So it says probability of sophomores out of the drama club. So in words, it says, what is the probability that a member of the drama club is a sophomore? So the drama club, that's the total we are talking about. Another way you can think about it is this is our population we are comparing. Okay. If drama club's the population, what's the sophomores? What'd you say? It's the sample, right? We're taking how many sophomores are in that drama club. Okay. Similar to the second one, your example 1B says it flips them. We're still comparing the same two events, just in a different way. So this time, the sophomores, that is our total, or our population. And then what's the drama? That would be our sample. Okay. So go ahead, this is your part A, this is your part B. Go ahead and find those different probabilities using the table. So if you look at your table, all right, so example 1A says, what is the probability that a member of the drama club is a sophomore? So here's our drama club. How many of them are sophomores? 3 out of 17. Good. So now part B says, what is the probability that a sophomore, so here's my sophomores. What's the probability that a sophomore is a member of the drama club? 3 out of, careful, 36 this time. And then remember, we always reduce when we can. So I'd get 1 out of 12. So let's talk about the difference of these. Right, but this time for the second part, we're talking majority, or we're talking about the sophomore population. So on part A, it says, what is the probability that a member of the drama club? So we're talking out of the drama club, how many of those are sophomores? That's where we got that 3 out of 17. On the second one, it says, what is the probability that a sophomore, so now we're talking about all the sophomores, what's the probability of a sophomore being a member of the drama club? So that's why we had the 3 out of 36 this time. Okay. Let's look at another example here. On this one, same example table that you have in example 2. It says the table below shows the vehicles in a parking garage one afternoon. A vehicle in the garage will be selected at random. So is there any bias here? Nope, because it's at random. Let B represent, so B event is the vehicle is black, and another event is the vehicle is a van. Are those independent? How we know if they're independent is we see if there's any overlap. So are there any vehicles that are black and a van? What do you think? So here's black, here's van. Right, there's overlap there. There's 3 vehicles that are both black and a van. Okay, so these would not be independent, they would be dependent. Okay, because there's overlap there. What is the probability of that then? Thank you. It says the vehicle is black and the vehicle is a van. So out of the black vehicles here, how many of them are vans? 3 out of 13, exactly. Yep. Okay, go ahead and try example 2. So you're going to say whether they're independent or dependent, and then tell me what the probability is. All right, let's look at this one together. First, let's see whether they're independent or dependent. So we have a vehicle that is red and a vehicle that is a car. Are those independent or dependent? Why dependent? Why is a vehicle that is red and a vehicle is a car dependent? There's overlap, right? Vehicle is red and the vehicle is a car. We have overlap there. Okay, so that's why it is dependent. So we want to know, out of the vehicles that are red, how many of them are cars? 5 out of 7. Yep. Okay. I'm going to ask this. What if I said, so you're telling me if it's independent or dependent. What if I said white vehicles and vehicles that are vans? Are those independent or dependent? Why are those independent? There's no overlap. There's 0 cars that are both white and both a van. Okay. Okay. What I want you to understand is we can also think of frequency tables as just little diagrams here. So notice, I know yours paper's in black and white, but notice how you have some that are colored, some that are not, right? So here, it says, suppose that you select one card at random. This at random is their bias. Nope. From a set of 6 cards below. It says, let B represent the event select a blue card, and T represent the event, select a card with a 3. Are these independent events? So one event is select a blue card. The other event is select a card with a 3. Are they independent or dependent? I heard dependent. Why? What do you notice out of your options here? Right. What do you notice about these cards? One's blue. They're both blue and have a 3. So there's overlap there. We selected a blue card and selected a card with a 3. Those are dependent on each other because they have overlap. Okay, what if I said selected a blue card and selected a number 4? Those are independent, right? Because there's no overlap there. Okay, so let's stick with this. Out of the blue cards, what is the probability that I draw a 3? 2 out of, think just the blue cards. 3. Yep, out of the blue cards, how many of them have the 3? Yep. So we are going to get more practice with conditional probability on an IXL. So go ahead and get your Chromebooks out.